This is the video lecture for the GPS and Mapping 2 lesson plan. It was created by Blake Liberati and edited and narrated by Sean Krupa. This video and accompanying lesson plan are part of Ohio University's Boat of Knowledge in the Science Classroom project, funded by the National Science Foundation. Before beginning this video, it is recommended that you have completed the GPS and Mapping 1 lesson plan. Let's begin with a review of mapping. Mapping has been an integral part of human history and dates back over 8,000 years. Maps are essential tools to help people define, explain, and navigate their way through the world. Now let's review GPS systems. GPS stands for Global Positioning System and was developed in the early 90s by the Department of Defense. GPS is made up of 24 satellites orbiting the Earth. And in order to triangulate any one location, you need 4 satellites. GPS systems work by continuously sending out signals to be picked up by receivers. The signals are sent at the speed of light, and the time it takes for each receiver to receive the message is measured. Now let's talk about map coordinates with an interactive example. How would you describe the location of a place? In the picture, we have Southern High School in Southeast Ohio. If you started by saying that it was in the United States, you'd be correct, but Ohio or Southeast Ohio would be more accurate. The real answer is an exact location. That's what we're after, and that's what map coordinates give us. In order to understand map coordinates, we need to review latitude and longitude. Latitude measures north and south of the equator, which is defined as 0 latitude. Above the equator is considered north, and below the equator, south. Conversely, longitude measures east and west of the prime meridian. The prime meridian measures 0 degrees of longitude. Left of the prime meridian is considered west, and right of the prime meridian is considered east. Here's a closer look at latitude and longitude conventions. Now let's review coordinate notation. The coordinates given below are read as 38 degrees, 58 minutes, 14.0 seconds north of the equator by 81 degrees, 54 minutes, 27.22 seconds west of the prime meridian. To understand degrees, minutes, and seconds, you need to think no further than of a clock. A clock has 60 seconds in 1 minute and 60 minutes in 1 hour. Similarly, on a GPS or map coordinates, 60 seconds make up 1 minute and 60 minutes make up 1 degree. It's important to remember that these are just different ways to say the same thing. There are 2 main notations for latitude and longitude. They are degrees, minutes, seconds, and decimal degrees, and you can easily convert between the two. So let's do some examples. We're going to convert the degrees, minutes, second notation of our 38 degrees, 58 minutes, and 14.07 seconds to decimal degrees. We start by converting seconds to decimal minutes. Take 14.07 and divide it by 60 and get 0.2345. The new notation then becomes 38 degrees and 58.2345 minutes. Now we need to convert minutes into decimal degrees. We take 58.2345 and divide it by 60 to get 0.9706 degrees. Finally, our coordinate in our new notation is 38.9706 degrees. Let's go the other direction. Let's convert decimal degrees to degrees, minutes, seconds. To convert decimal degrees to minutes, we take 0.3303 degrees and multiply by 60. This gives us 19.82 minutes. At this point, the new notation would be 39 degrees and 19.82 minutes. Finally, we need to convert decimal minutes to seconds. We take 0.82 minutes and multiply by 60 to get 49.2 seconds. Finally, our new notation in degrees, minutes, and seconds is 39 degrees by 19 minutes by 49.2 seconds. At this point, we've concluded the review of GPS and Mapping 1 main points. If any of this is unclear, you should pause the video and review. Continue the video when you're ready to resume. Now we're going to talk about the science of GPS systems. Shown on the screen is the most famous scientist of all, Albert Einstein. But why Einstein? Let's review Einstein's main contributions to science before going any further. The first and most famous is probably his energy-mass equivalence equation, E equals mc squared. But Einstein is also known for photons in the photoelectric effect, which says that light shined on the surface of a metal can dislodge electrons. Are we forgetting anything? Is Einstein known for anything else? If you said relativity, you're correct. Einstein's theory of relativity has two parts. One is special relativity. Special relativity looks at the physics of objects moving near the speed of light. General relativity, on the other hand, deals with space and time and their relationship. So what does this have to do with GPS? Satellites orbiting the Earth are traveling at a speed of 14,000 kilometers per hour. While this is nowhere near the speed of light, it's fast enough for special relativity effects to be considered. Also, satellites are orbiting at an altitude of 22,000 kilometers, which means the pull of gravity there is essentially zero and much different than the gravity of that on the Earth. Therefore, general relativity effects are seen. So what does this mean? We said that GPS satellites are fast enough and high enough to feel both types of relativity. It follows that GPS systems need to correct for relativity. And finally, and most importantly, GPS systems are proof that Einstein was right. So just how much do we need to correct? This circle is centered on Southern High School that we talked about earlier. Without relativistic correction, a GPS unit would give the location of the high school to be anywhere within this circle, as much as 10 kilometers off by its true location. At this point, we're going to watch a video produced by Canada's Perimeter Institute on GPS systems, Einstein, and relativity. Ohio University Books purchased a digital license for this video, however, it is not to be copied or distributed.
It's a navigational tool used by millions of people every day. With it, drivers know where they're going. Pilots fly planes more safely. It helps construction workers build straighter roads. Farmers plant fields more efficiently. Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS.
So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you would have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high, and also it's measuring time. You have 4 satellites. They're sending you signals, and you're measuring accurately where the satellite appears to be and when the signals were sent. And from that, you can figure out where you are on the Earth's surface.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal traveled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters.
To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created.
The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day.
After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitation theory.
Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds fast every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
The effects of relativity on Earth are normally 1 part in 10 billion, and so that's an incredibly small effect, and you're used to thinking you can forget it for most things. But when you're relying on how far light travels in a particular amount of time, if you're wrong by even microseconds, then the distances that you're getting wrong are that much larger.
To correct this error, engineers adjusted the atomic clocks inside the satellites, so on Earth they ran slow by 38 microseconds per day. This compensated for the effects of relativity and meant that, once in orbit, the clocks ran accurately, giving us the powerful tool we have today. So, as you see, what began as an abstract theory over 100 years ago is now used in everyday technology. Every time you use GPS, you're using relativity. Whether you're heading out to meet friends, trying to find the nearest movie theater, or looking for a restaurant in another country, you'll always know where to go using GPS.
So relativity is not just something to study in school. It actually affects daily events in people's lives. Your life.
It's very amazing that after they were developed, they became such an important factor in designing GPSs and navigation systems. And basically, we would have been able to do them if we didn't know much about relativity.
On the one hand, you might think of Einstein's theory of general relativity, this theory that space and time are warped. You live in a 4-dimensional space-time. You might think that that's the part of physics that's furthest away from day-to-day life, and yet it shows up in this fundamental way in GPS technology, which is crucial to everyone's day-to-day life at this point.
Theoretical physics, closer than you think.
In summary, we reviewed GPS systems. They've been fully functional since 1994 and include a system of 24 satellites to triangulate locations. We reviewed the 2 types of map coordinates, degrees, minutes, seconds, and decimal degrees. And finally, we saw that GPS is a demonstration of Einstein's theory of relativity. This concludes the video lecture for the GPS Mapping 2 lesson plan. Thanks for your attention.